Today we will explore the photoelectric effect, a fundamental phenomenon in quantum physics that demonstrates the particular nature of light. We will discuss key experiments and theories that contribute to our understanding of this effect, including the Hawage effect, Lennard's experiment, Einstein explanation, Millikan confirmation, and the key characteristics of the photoelectric. We will also the classical and quantum model of light. First, Hawage effect. Let's begin with Hawage effect. This phenomenon occurs when ultraviolet light causes a charged object to lose its charge by emitting electrons. Heinrich Hertz first demonstrated this effect in 1887 by using a spark gap apparatus. He observed that sparks jumped more readily when the electrodes were illuminated with UV light. This was one of the first indications that light could influence the property of metal, setting the stage of our understanding of the photoelectric effect. Next, we have Lennard's experiment, conducted in 1902. Lennard investigated the relation between light intensity and results of photocurrent. He discovered that increasing the intensity of light increased the number of emitting electrons, while the kinetic energy of those electrons depends on the frequency of light, not its intensity. Lennard's findings provide critical evidence supporting the particular nature of light, which was essential for the development of the photoelectric theory. In 1905, Albert Einstein proposed a groundbreaking explanation for the photoelectric effect. He suggests that light is composed of discrete packets of energy called photons. The energy of the photon is given by the equation E equal to hf, where h is Planck constant and f is the frequency of light. Einstein also introduced the equation Ek equal to hf minus W to describe the kinetic energy of emitted electron. Here, Ek is maximum kinetic energy of an electron, hf is the energy of the incoming photon, and W is work function of the metal, which is the minimum energy required to release an electron. Today we will explore the photoelectric effect, a fundamental phenomenon in quantum physics that demonstrates the particular nature of light. We will discuss key experiments and theories that contribute to our understanding of this effect, including the Hawage effect, Lennard's experiment, Einstein explanation, Millikan confirmation, and the key characteristics of the photoelectric. We will also the classical and quantum model of light. First, Hawage effect. Let's begin with Hawage effect. This phenomenon occurs when ultraviolet light causes a charged object to lose its charge by emitting electrons. Heinrich Hertz first demonstrated this effect in 1887 by using a spark gap apparatus. He observed that sparks jumped more readily when the electrodes were illuminated with UV light. This was one of the first indications that light could influence the property of metal, setting the stage of our understanding of the photoelectric effect. Next, we have Lennard's experiment, conducted in 1902. Lennard investigated the relation between light intensity and results of photocurrent. He discovered that increasing the intensity of light increased the number of emitting electrons, while the kinetic energy of those electrons depends on the frequency of light, not its intensity. Lennard's findings provide critical evidence supporting the particular nature of light, which was essential for the development of the photoelectric theory. In 1905, Albert Einstein proposed a groundbreaking explanation for the photoelectric effect. He suggests that light is composed of discrete packets of energy called photons. The energy of the photon is given by the equation E equal to hf, where h is Planck constant and f is the frequency of light. Einstein also introduced the equation Ek equal to hf minus W to describe the kinetic energy of emitted electron. Here, Ek is maximum kinetic energy of an electron, hf is the energy of the incoming photon, and W is work function of the metal, which is the minimum energy required to release an electron.
For photoelectric problem, the first problem is about why was the wave nature of particle not discovered until atomic level experiment became possible. For the first reason, it is hard to observe about wave-like property of the large objects in our daily life. The second reason is about technology isn't enough for detecting atomic scale experiment in that era around 20 until 20th of century. And classical physics problem only observe about large object that they can easily to observe before discover about quantum theory. The next question, what is the frequency and the wavelength of a photon energy of 4 electron volt? We use the formula E equal to hv. E is the energy of the electron that has 4 atoms, and h is Planck's constant that we know that it is 6.6 multiplied by 10 power minus 34, and use V equal to E divided by h, and we get the answer that it is 9.7 multiplied by 10 power 14 Hz, and use the formula C equal to lambda V. Lambda equal to C divided by V, that is the speed of light divided by frequency that we earned from the previous question. Then we arrange unit of our answer and get 310 nanometer. For the next question, a light source of frequency 4 multiplied by 10 power 14 Hz has a power of 2 watt, 5 numbers of photons emitted per second by the light source. If photon equal to hv equal to 6.6 multiplied by 10 power minus 34 and multiplied by 4 multiplied by 10 power 14 equal to 2.64 multiplied by 10 power minus 19 joule. Next we find about numbers of photons per second, and we use the formula P divided by E, and we get 2 divided by 2.64 multiplied by 10 power minus 19 equal to 7.58 multiplied by 10 power 18 photons per second. Thank you. Good morning everybody, my name is Rangsiman Arya Sunthorn from Compton with Science Academy M6. Today I will present about one of the topic of the EM wave that called Compton effects. All of these are topics that I will present today. There are Rayleigh scattering, Compton scattering, and comparison between both topics. The first topic is about Rayleigh scattering. Rayleigh scattering is the scattering of light or other electromagnetic radiation by particles much smaller than the wavelength of the radiation. It occurs when light interacts with molecules or small particles in a medium such as atmosphere. For example, we can see the sky is blue color. That is one of Rayleigh scattering in our everyday life. Key characteristic of Rayleigh scattering. Particle size is smaller than wavelength. Intensity is inversely proportional to wavelength power 4. It is elastic scattering, angular dependence, and effect on different wavelengths. For the formula, first we can see that intensity is inversely proportional to lambda powerful, as I mentioned before. Then we can study about formula that is I equal to I0 x pi power 4 n alpha power 2 divided by lambda power 4 and r power 2. And all of this multiplied by 1 plus cos theta power 2. N is the number of scatterers, alpha is polarizability, and r is distance from scatterer. And as I mentioned before, I is inversely proportional to lambda power 4, that is due to this equation 2. Next topic is about Compton scattering. Compton scattering is the phenomenon where high energy electromagnetic radiation collides with a free electron, resulting in a change in the direction of energy of the photon and ejection of the electron. From this picture, you can see that about high energy of proton clash with the electron shell in the outer shell, and it will result that the proton will bend from its way from theta angle, and the electron will be removed from the shell too. Key aspect of Compton scattering: photon and electron interaction. By clashing, that proton lost its energy to electron. Energy and momentum conservation, that is inelastic collision that lost energy. Wavelength and energy shift of this equation, and evidence about property of light. This is Compton formula, that is delta lambda, or difference between lambda final and lambda initial, equal to Planck's constant, or 6.626 multiplied by 10 power minus 34 June 6, and divided by m is the rest mass of the electron, that is 9.109 multiplied by 10 power minus 31 kilogram, and speed of light, or c, that is 3 multiplied by 10 power 8 meters per second. Then all of these multiplied by 1 minus by cos theta, or cos of scattering angle. Next topic is about important equation of Compton formula. For the first is P equal to E divided by C, and E equals to HV. And then V divided by C equals to lambda, so P equal to H divided by lambda. Lambda final minus by lambda initial equal to delta lambda, and delta lambda equal to H divided by MC, and of this multiplied by 1 minus cos theta that I have mentioned before. The upper equation, that is the recoil of electron equation, is P equal to root E power 2 minus by M power 2 and C power 4, and all of the root divided by C, or speed of light. And the lower equation, it is same to the first equation, that is the scattered proton, but it is post collision, or the final proton. These are comparison between both topics. For type of interaction, Rayleigh is elastic, but Compton is inelastic. Particle size: Rayleigh scattering occurs with particles much smaller than wavelength, but Compton scattering occurs with free or loosely bound of electrons. Wavelength dependence: Rayleigh scattering is stronger for shorter wavelength, that is inversely proportional to lambda power 4. But Compton scattering wavelength shift depend on scattering angle. Energy of radiation in Rayleigh is visible and infrared, that is lower energy than Compton, that is X-ray and gamma. And effect on wavelength: Rayleigh don't change any wavelength, but Compton scattering wavelength change with scattered proton increase. An application of Rayleigh scattering can use to explain blue sky and resonances, and even optical physics. But Compton scattering used for explain quantum mechanics, X-ray and gamma ray interaction. Thanks for listening. Thank you.
For the problem about the Compton effect, first one, using Compton's conservation of energy and momentum, give an expression for 1 over p minus 1 over p0 as a function of electron mass and angles theta. First, the photon energy E equal to hf equal to pc. The next one, the initial condition E0 equal to hf0 equal to p0c. According to the energy conservation, E0 plus m electron square c equal to E plus E of electron. And from the momentum conservation, P0 is equal to P plus the P of electron. So we're gonna get the final results as 1 over P minus 1 over P0 equal to H over MEC times 1 minus cos theta. To the next section, from the first one, expression for the Compton formula. We get that P equal to H over lambda. So as substitute into the expression from the last part, 1 over P equal to lambda over H, and 1 over P0 equal to lambda 0 over H. So we got the equation that lambda over H minus lambda 0 over H equal to H over MEC times 1 minus cos theta. So we get a Compton formula as delta lambda equal to lambda minus lambda 0 equal to H over MEC multiple with H over M is H square over MEC times 1 minus cos theta. For the next one, we observe the Compton effect with the visible light, so we need to calculate this first by the scattered angle lambda is 180 degree. H equal to 6.626 times 10 to the power of minus 34 joules. And mass of electron equal to the 9.109 times 10 to the power of minus 31 kilogram. And C equal to 3.00 times 10 to the power of 8 meters per second. For the formula, lambda C equal to 6.626 times 10 to the power of minus 34 over the 9 times 9.109 times 10 to the power of minus 31 times 3.00 times 10 to the power of 8 equal to 2.43 times 10 to the power of minus 12 meter. This is the Compton wavelength. So the wavelength of the visible light is between the 400 to 700 nanometer or 10 to the power of 17 meter. This This is smaller than the visible light, so we can observe this in the visible light condition. The next one, we need to explain why the X-ray wavelength need to observe this. From the last one here, wavelength of Compton is the 10 to the power of minus 12 meter. And the X-ray is between the 10 to the power of minus 10 meter. The visible light is between 10 to the power of 7 meters, so the wavelength shift that is too small to detect with the current instrument. So the X-ray used to observe the Compton effects because the shift was significant and measurable. And the last one, calculate the predicted wavelength shift at theta of 138 degrees for the X-ray wavelength. So we got the wavelength is the 0.0711 nanometer. So given that it is a 7.11 times 10 to the power of minus 11 meter. The scattering angle is the theta as a 135 degrees. So the cos theta is equal to the minus 1 over root 2. The Compton formula, delta lambda is equal to h over the MEC times the 1 minus cos theta. Substitute the nose value, so we get that the delta lambda is 2.43 times 10 to the power of minus 12 times 1 minus 1 over 2 root of 2. So we get that 2.43 times 10 power of minus 12 times 1 plus times 1.707. So it's approximately 4.15 times 10 power minus 12 meter. So the predict shift of the wavelength is approximately 4.15 times 10 power minus 12 meter, or 0.00415 nanometer.